of AlphaGo and AlphaGo 0, okay, we discussed about models that work on low-dimensional states, and the input is in a low-dimensional state, and the output is again the same low-dimensional state, all right? And then you feed your input, your output back as input, and you do unrolls. This precisely is PETS. Pretty important work. You will see in the homework. Model-based reinforcement learning on sensory space, and we discussed directly observations and feedback their observations back as input. And you pointed out that pixels have a lot of information that is actually task irrelevant, and by forcing the model to predict in a pixel space, and I mean, you really suffer. You really need to model things that are super relevant to your task and potentially are extremely hard to model the dynamics of, for example, clouds or anything else. And last time, we also discussed about latent space models. We said that there is this choice that instead of predicting pixels, you can jump in latent space and predict recurrently, like feedback predictions, unroll your model in that latent space. And we saw that actually there's nothing wrong with this. This is not the model is still okay. And we said that to do such a latent space unrolling, right, and training, and not to have the collapse where all the latent vectors are mapped to the same zero vector, you need to predict some task relevant or task irrelevant quantities. I remember your colleague very correctly said that if you just encode your current observation and past observations into a vector, feed this into the dynamics model, predict the next latent vector, encode your next observation into a latent vector, and make sure you just minimize that L2 distance on that latent space, totally, the model can just map all future vectors to zero, right? So we want those latent features to capture task-relevant quantities. Before people realizing that, actually you can train these latent models by asking them to predict task-relevant quantities only, such as rewards, policies, Q values, they were training so that those latent features actually generate semi-relevant quantities, for example, reconstructing back the image pixels. So what have you gained? Well, you don't predict images and you feed images back as input. You still predict latent vectors, which are actually decoded into images, and there is an extra reconstruction loss right there. Okay, so essentially you train for auto-encoding, you go to the latent space and that latent space better decode back the input. And because you ask the model to actually predict the observations, you don't have this collapse problem, right? Another obvious thing would be, you know what, I hate the image reconstruction task. Again, I need to be predicting, reconstructing things, keeping in my latent vector, things that are irrelevant to my task. And I do not like that. So the only thing I'm going to predict from my latent vector is reward. The problem with the reward is that it's too sparse. It's just not enough information for you to train a very reliable dynamics model. Okay. All right. So now there is a difference between autoencoding objective and predicting the future in pixel space. Autoencoding simply means that your latent vector should have the whole information as the current image. So if you see clouds in the current image, despite the fact that clouds are irrelevant to your task, this cloud information should be retained in the future vector because you'll try to decode the clouds back. That the good thing, though, the difference between this autoencoding objective and predicting the next image, okay, is that you don't need to model the dynamics of the clouds. Do you see what I mean? Yeah. Now, or at least you don't stress the model too much to predict the dynamics of the clouds, because your dynamics model still needs to predict the latent vector of the next frame. And if that latent vector has retained cloud information in some part, then of course your dynamics model needs to actually capture that. But because it's not in a pixel space and it's a latent feature vector space, but this humongous chunk of sky can go and be placed into a small part of the feature vector, let's say. Okay. Now, so this is about image reconstruction objectives. So we'll go back to that. By the way, I think we may not have time to do this today, but Monday, we will talk about latent dynamics models that model dynamics in the latent space coupled with image reconstruction objective. Okay, so this is Dreamer version 1. and Dreamer version 2. And actually, you'll see some very nice images and at the same time, extremely good performance for playing Atari games. Okay. All right. So today, though, we'll talk about latent dynamics models without image reconstruction objectives, simply by predicting task-relevant quantities. Okay. Rewards, Q values, and policies. This is a paper that we started to discuss last time. So this is the first thing that we're going to visit. Do you have any questions so far? Okay, any form of questions like logistical questions, anything you want to ask? Okay, so let's see. Why we like this paper? Well, we like this paper because it's actually extremely similar to PETs. Again, we're going to be learning actions by sampling trajectories. All right, exactly what PETs did. But instead of having our dynamics model predict the input, the input raw, let's say observations, which can be either a low dimensional state or an image, instead we're going to go to a latent space. But other than that, the things are going to be very, very similar. We're going to have an initial state as 0. We'll be able to unroll trajectories for some temporal horizon. Sample many of those trajectories. There's going to be optimization over the actions that you need to do to land to a trajectory that has high, let's say, fitness, which means high reward. And then based on these actions, bootstrap yourself and, improve your policy and so on. So similar to PETs, we're going to be using a learned model of the environment. Okay. Our goal would be to compute actions that have a high sum of future discounted rewards. And here it says that this is intractable because if your horizon is very large, right, infinite, clearly we cannot do it. Clearly we cannot unroll trajectories that are extremely, extremely long. Is that clear? So what are we going to do instead? Well, we're going to truncate our horizon. We're going to pick some capital H that we feel comfortable optimizing. And then this is, this is the maximum length of the trajectory unrolls. And they have very nice, let's see. So yes, the major challenge is compounding on model errors and cost of long horizon planning. So now instead of doing long horizon planning, you're going to plan only up to some type step H, okay? And now a big question, one thing that they do at least, is how do you compute then the cost of a trajectory that is only H time steps long, okay? If your task really is of, much longer horizon. And this is their first contribution, okay? They're going to add the terminal value function, okay? So model predictive control or this trajectory arrows that we said yields, if you don't do any modifications, if you just score the trajectories based on sum of time step rewards, the only thing you're going to do is going to find a trajectory that is actually the best for the number of time steps that you consider. Let's say your real task horizon is 400, but you don't have time, so you only pick 40. If you evaluate trajectories based on the sum of rewards of those 40 time steps, what you're going to find is a locally optimal solution, locally in terms of time. The best actions for the next 40 steps. But this is not what you want. What you want is what is the 40-step trajectory that actually does well in my 400 horizon task. Is this clear? So what do you think we should do to achieve that? Well, the solution has to do with how you will evaluate a trajectory. So instead of evaluating a trajectory simply by considering the rewards that you get on the H first time steps, we're also going to add an evaluation of the last time step of the trajectory that doesn't take into account the reward, but takes into account the Q function. And what is a Q function? A Q function is the expected future returns. All right, so we'll be estimating a Q function. And when we're optimizing for trajectories, the fitness of a trajectory will be sum of instantaneous reward plus terminal Q. Okay, which I don't think is super surprising, right? This is precisely what, it makes sense. If you have a Q estimate, why would you not add it to your trajectory? All right, now let me ask, who is going to give you those rewards? Those are thetas. Who's going to give those are thetas? Yes. The what? That we're going to train. Exactly. So just do not forget that all this optimization happens in your head. It's a mental optimization. You don't act in the environment. You're just thinking. You have a dynamics model that predicts rewards. You have a Q function, and essentially you just do an evolutionary search to find the best possible trajectory to play for the next capital H time steps. Okay. All right. Yes.
Why is the Q at the horizon instead of like a value at horizon plus one per se? What's the benefit of training a Q, which seems harder, rather than training a value function at the end of the horizon?
So Q and value function are, by the way, identical. Very similar. The only difference between V and Q is that Q is conditioned on an action, right, and V is conditioned on the state. Because here we care about obtaining actions, right? It makes sense to use the Q. Now you may say, excellent question. So our argument earlier in the course was the following. We don't use value functions because to use a value function to select actions, you need a dynamics model that tells you I'm in this state. Here are my action possibilities. My dynamics model will tell me what is the resulting next state. By evaluating the value of the resulting next state, you take the argmax and say, oh yeah, action 3 landed me in a state that my value function picked. Well, there's no reason to do that one step look ahead if you have a Q value, a Q function. Is that clear? And there is nothing simpler on training a V versus training a Q. It's just an extra conditioning, the same training data and the same bootstrap method you're going to do. Do you agree? It just is computationally efficient not to do that one step look ahead. Although in this case, yes, you can do it because we have dynamics models.
Okay.
Is that a good?
Yeah.
Okay. Yes?
How do we handle the compounding uncertainty in the model being like inaccurate?
Yeah. So our model will be inaccurate. Okay, as your colleague is saying. We jump to a latent space and we ask that latent space to only predict task relevant quantities, which I'm going to show. Aside of that, we do model predictive control, which means what? We plan for capital H, future time steps. We think, we sample trajectories, we optimize. I'll show you exactly how this is done. Then I get 40 actions. I'll execute the first one. I'll land in a new state, and then I'll replan. This is model predictive control. So it's not like I get my 40 actions and I go and, open loop execute them, because indeed, the last actions probably are going to be wrong because the model errors accumulate towards the end. But yes, this is what we're going to do. Okay. Other questions? Okay. So here's the observation. We jump on the latent space. We do planning with a learned model. We look at the final Z dates is the resulting state. We look at the reward plus value. This is how we evaluate our trajectories, right? And based on this optimization, this whole optimization, we call it planning. We select an action, we act in the environment, we get a reward, and we change the state, and again, we plan again and act again and so on. Do you see? All right. Planning in a latent space. So this planning is very similar to, it's a search process. Before we were using Monte Carlo research. Now we just have a much simpler trajectory sampling. So we'll go into details in that process. And this is precisely how we do that planning. Okay, which we call it inference. So how does this happen? So here are the details, which I think are pretty nice. Again, they have so here is their first contribution. So you are in particular state S, and this can be a low-dimensional state or an image as you see the extension later. But no matter what it is, you just pass it through a representation network, okay? Now, if you have images and if you have low-dimensional states, you're going to use different H's, but the rest of the algorithm stays the same. Only the encoder changes. So you jump into that space Z, and then what are you going to do? Till capital J. Yeah, I'm not sure why capital J now needs to be. The iterations of, this is the iterations of the optimization cross-entropy method. Okay, so what do? you sample some actions. That's how we start in CEM, right? We instantiate some mu's for the actions at every time step. And those mu's start from being exactly identical. These are the mu's and sigmas. These are the Gaussians where you sample actions at every time step. They start by being all the same. Mu 0 is 0, but then they are thus diversified during this cross-entropy method, right? You're updating the means and the variances of these Gaussians where you sample the actions. And the interesting thing here is you sample some trajectories randomly because you understand that those Gaussians are completely random when you start your planning process. And then you sample some trajectories by asking your policy, pi theta. So you both have a policy, but you also sample randomly. Why should we do that? Why you think this is a good idea? Yeah?
Allowing for exploration.
Yes, to be honest, yes. So that's very important actually, because usually our policies, usually we use Gaussian policies, right? So they cannot be extremely diverse. And at training time, you really need to search everywhere to find the right solution. Okay? Does this make sense? So it's very important, and they present this as a contribution of their paper. When you sample action sequences, action proposals, okay, because CM is about proposals and then evaluating those proposals. Yes.
Is there a reason why it's like n fully random trajectories and then n policy trajectories rather than like an epsilon self version of the policy?
Yes. Okay. So this is a question. So your colleague says, why don't we just take our policy network and add residual noise to the predicted actions of our policy, as opposed to having a very separate, sampling really, really randomly. Let me think. If your Gaussians are as wide as the first ones, I don't think it's going to be very different. Okay? Because if you still have as wide Gaussians as what you have here, then whether you center them at the predicted actions or not, it might be the same. Yeah, actually, no, I didn't like that. Let me tell you, when you sample from your policy by mutating those actions, in any case, you will search around your local predictions of your policy. So you want to search far away from what your policy is predicting. Is that clear? So by sampling some trajectory proposals from your policy during the cross-entropy method, during evolutionary search, some of those may succeed and do well, and they're going to be mutated, and you're going to be searching nearby and updating your fitness and so on. So you also want to search some trajectories that are really far away from what your policy, suggests, correct? Yeah. Okay, wonderful. So once we have sampled trajectories, what do we do, guys? So we have now some, I think, genotypes. We just sample those guys, right? Is this 100% clear? Okay, so who wants to tell us how long is a trajectory? Like what is the shape? What is the number? How many numbers are there in one trajectory? What's exactly, yes? Capital H. Within every time step is what? Is one scalar or what?
There's the reward that you predict with the reward.
But what is a trajectory, I'm trying to say? So, for example, when we did evolutionary search for policies, our genotypes, whatever we're searching over, were the number of parameters of our neural network. What is now the numbers of parameters over which we're searching?
The number of values in the state vector, correct?
Okay, let me ask something else. In pets, what we were searching over? What were the proposals? Yes.
We were searching over action sequences.
Action sequences. Great. And how long were those action sequences? Like how many numbers you have there?
Capital H.
Capital H, and within every time step is what you have?
You have like one scalar for one, like
But that's not true, because my action, if I'm a robot, right, it needs to be, okay, where all my joints should be. So an action may have multiple parameters. So maybe what you want to say is the number of parameters that you need to describe an action by the number of time steps. Is this what you're saying? This is what we mean here, guys. We're searching over action sequences. This is our proposals. Okay, is this clear? This is very important. So this is great that we asked. So the planning, let's see again this nice visual. Oh, I don't see. Oh, here it is. This is what happens with the cross-entropy method. And these are just plans. the dynamic parameters are constant, frozen. We're only searching over action sequences, okay? And that's exactly what we did with pets. Again, with the learned dynamics model, that was not over the latent space, was over the input low dimensional state space, which is the low dimensional state space, the configuration of your robot, where the objects are in the environment, XYZs, stuff like that. Is this clear? Okay, so these are our action sequences now. And I want to ask you, how long is this mu J? Okay, J just think this is the iteration of the evolutionary search, okay? First iteration, second iteration, how many iterations you're going to do for your search method. How long is a mu J? Yes, the dimension of the action. Yes, so I think they mentioned in the paper that, of course, you're going to have different mu's per time step, right? Because what action I need to do in this time step is very different than the action I'm going to do in the next time steps. So naturally, you have different Gaussians for every time step. They all can start from the same thing, maybe around 0, whatever. But then through search, the mu's of those Gaussians change. Is that clear? Yes.
Also, the normal distribution is not like the vector of actions.
Yes, you can think of it like that. It's a Gaussian that has the vector of actions at all time steps. Okay, so it's a big Gaussian that has where you sample actions for every time step. Okay.
Okay, but we sample for each time step at once, or is it like we sample each time step separately?
Okay, so to be honest, the notation in the paper shows mu JT, for example. There is a subscript T that denotes for which time step it is particular Gaussian. So you have them separately, and you just sample from them separately. That's how they, okay? Is that clear? Yes.
Where are the parameters of the Gaussians stored?
Okay, let me tell you, these Gaussians, these means and so on, there is not a neural network. It's just you directly, the free variables are directly those means. Do you see? You are updating directly these Gaussian means and variances. Is that clear?
Yeah, at that moment you're doing it.
I mean, you start from whatever. Let's say my action has, let's say, 5 dimensions or 7 dimensions, like with my joints where it needs to be and so on. So you start with some Gaussian that is 0 length of 7. So you have 7 zeros, okay? And by adapting it over time, this mean moves around. Is that clear?
Yeah, my understanding was that there was a different Gaussian for every action.
For every time step.
For every time step.
Yes.
And then
so you're updating those means. Those means move around.
Between time steps.
And across iterations, okay? Across iterations, as you're iterating through the evolutionary search, the means, right? What the evolutionary search searches over is the means of those Gaussians where you sample your actions from.
Oh.
Okay, this is precisely what we're search over.
Yeah.
Okay, this is what we're updating.
Yeah.
Okay. All right. So basically, you sample a bunch of trajectories. You keep the top elite, top 30. Then you're updating those means at every time step based on the elites. Okay, and then you sample again, and so on and so forth. Right. And the only thing that they change is that not only you sample from those guys, but you always initialize those trajectories from action sample from your policy. Yes.
So for like line 4, just to confirm, are we sampling those trajectories using our model of the environment or the environment? Maybe I'm misunderstanding.
Great. So when we sample trajectories and we're trying to optimize over those actions, okay? Are we using the actual environment or we're using our learned dynamics model of the environment? Yes, we're always using the learned dynamics model of the environment, right? Otherwise, this would not have been possible. This requires resetting, so you always need to be in the same state, and then you need to sample tons and tons of trajectories. This is very, very, very costly. It requires insane amount of interactions to actually use the environment. The whole point of using the dynamics model is essentially to do action selection through unrolling. That's one way we said we're going to be using dynamics model. We presented 2 ways that we'll be using dynamics models to improve our policies. One was, who wants to say, I'll say the first. So the first is exactly what we're doing. We unroll and we optimize over action sequences. And what was the second one that we also have seen already? We've seen quite a lot. So either we unroll forward and then we optimize over actions. So we call this model-based control. That's how we called it. And the second one was what? Yes.
Training in the absence of planning.
Training, and how do we train in absence of planning using the model?
We sort of update our policy using the results of sort of simulated sequences.
Okay, yeah. So your colleague is saying that we're going to use the model to sample synthetic experience from. We're going to throw the synthetic experience along with real experience, a big experience buffer, and we're going to use a model-free policy. And if you remember that model-based reinforcement learning in Atari that we saw was actually training a model, was sampling from it, dumping it in a buffer, using PPO, and actually got results that were better than a method that didn't use this extra model learning plus synthetic experience sampling. Is that clear? Now, is this what you wanted to say?
Yeah.
Yeah. Do you guys agree? Yeah. And when you sample synthetic experience, there's no planning. By planning, we mean look ahead. So essentially, you enroll, you try to look at the future, you estimate your fitness, you see based on where you landed, which one of those, trajectories were the best, and then you select the action that corresponds to that best trajectory. Okay? Do you see the difference between planning and just sampling experience from the model? Okay. All right. So now we have our trajectories. We initialize them. Then here what happens is we evaluate what? Their fitness score. We evaluate their fitness score. Now I want to ask you, what we have sampled is action sequences. Now from those action sequences, I need to get what? Corresponding states where those action sequences are going to take me. I have my Z0, but I want to see what is the resulting state sequence as well as the resulting rewards of those sequences. How we're going to do that? I give you a bunch of actions, one for, yes?
You've got a forward dynamics model that takes on the previous latent state and the action representation.
And gives you the next state, right? And then you feed there your other action because you have a whole action trajectory, and then get the next state and so on. And you also get the corresponding reward, correct? So you have everything you need to, go from sequence of actions to sequence of states and to sequence of rewards using your learned dynamics model, all right? And so also you have a Q function, which we're going to show how you're going to train with the standard, with the standard targets reward plus gamma of the Q of the next state. And now you have everything you need to do what? To estimate the fitness of those trajectories. This is very important. Otherwise, how are you going to do evolutionary search? We have the genotypes, right, which are start from sequence of actions. We feed them in our dynamics model. Now we have sequence of states and rewards. And we have also the Q for our terminal states. And now for each of my action sequences that I sampled, some from my policy and some from randomly, I have fitness scores. So now what I'm going to do? Well, I'm just going to update my mu's and j's and sigma j's for the next iteration. That's precisely what we did for evolutionary search. We're updating the parameters of the Gaussians where we were sampling our proposals. And essentially, they do a weighted sum there. They don't have a threshold with elites. They just have a weighted sum. Much like our natural evolutionary strategies algorithm. Okay? Is that clear? All right. So now that you updated your mu j's and sigma j's, you go back, you sample again from them, you sample some trajectories from your policy, and again you search, etc., till you land to the best possible parameters. Okay. And then essentially once here is at the end of your iterations, the mu capital J, sigma capital J, and essentially your actions are going to be sampled from those resulting Gaussians. Is that clear? So this is the inference part. This is just this part, the planning. Once you have a dynamics model, how do you generate actions that actually maximize rewards in the terminal Q? Is that clear, guys? Now, the interesting thing is that if some of your trajectories here that you sample from your policy score highly, clearly those are going to influence the mu's directly, right? Because you take a weighted sum, essentially the mu is a weighted sum of the best performing actions every time step. weighted by their fitness score. So clearly, if the actions you sample from your policy are the best performing, the mu's are going to shift towards those immediately. So you don't need to actually sample from your actions with added noise, because actually this happens immediately. Yes?
Why do we in the end need to sample? Like,
Okay, you can take an arg. Well, why you need to sample?
just take the mu, because we were inference, right? We don't need to explore.
I agree. At test time, you don't need to explore. You just take the argmax. I totally agree. But that inference loop also happens at training time. Okay. Let's see. Okay, so this is good. We said about that. This is the cross entropy method, sure. Okay, so now we know about the inference. And now we need to talk about the whole training of the model. Okay. So the idea here, as you say, model only the parts of the amounts that are predicted of the reward. This is going to be precisely what? Rewards, policies, and cues, and learn jointly the value function using TD learning. So here is how things look like. Okay, let me play again. Yeah, so basically you learn a dynamics model that from that latent feature vector predicts the value and the reward and the policy. And by the way, this idea was proposed first in mu0, which is the next paper we're going to see after that. And actually, even the pictures looks very similar. And this is extremely transformative idea. Okay. Yeah, this is super transformative idea. And the new thing here, though, which is very, very important. All right. The new thing is the following. You're going to take the next time step and you're going to encode it and you're going to train your latent dynamics model with consistency. All right. This was not there in mu0. And actually, this can drive the number of examples that you need much lower. There is, though, a much recent paper called efficient zero, which is exactly mu0 plus this added loss. Okay. And I'm going to show you exactly what is that added loss. Something actually that you really, really are familiar with, which is the following. So this is my the latent feature vector of the current time step and the action, and I feed it into my dynamics model. All right, and this will predict the latent feature vector for the next time step. And what I want to make sure is that predicted feature vector is actually indeed consistent with the encoder for that next time step, h theta minus. And what is what is theta minus? Is exactly theta, but a much slower updated theta. Every now and then, much like in deep Q learning, the theta minus will copy paste the parameters of the theta, or it's updated with a moving average and so on, just to have a constant targets. Is that clear? So this is exactly what we saw, if you remember, in the last lecture, and your colleague said, oh, but this can default to mapping everything to 0, which is exactly correct. Now is not going to default to mapping everything to 0 because you're asking it to predict Q values and rewards. Is that clear? And actions. So from that latent feature vector, you'll predict all your task relevant quantities. All right, so let's see how you do that. We know how to do this. This is just a standard regression. Okay, this is also a standard regression. So you have different time steps and you know the actual rewards. So you train your model, R theta, to predict rewards that actually match the actual rewards Ris. And here is how you predict your Q value, which is with Q targets being the immediate reward plus gamma Q of the next time step. And here for the next time step, you actually feed the action of your policy. Is that clear, guys? So you just put our term about consistency of the dynamics of the latent feature vectors you're predicting, along with predicting the reward and predicting the Q value. All right, so let's see more details of that. So what does the policy minimize? It minimizes the Q values. This is very, very similar to DTPG, essentially because your dynamics model, so your policy is actually deterministic. You can propagate through the Q function to update the parameters of your policy. So here is a more detailed description of the training loop. All right. So here is the theta and the slow version of the theta. And while not tired, so you just keep doing this for as much as you like, you collect episodes using the TD MPC, whatever we discussed earlier, and you sample actions through that planning process. This is very, very similar, guys, to what? The AlphaGo Zero. If you remember, the way we collected experience was not by sampling from our policy. By the way, sampling from your policy doesn't require any thinking. It's just reactive, right? You have your policy network, you see the current state, you feed it, then you say, okay, here's my action. But here, we don't do that. To be able to act at training time, while you're training yourself, you need to think. And you remember what we said with AlphaGo Zero? 0.4 seconds to think about one action. Okay, so this guy takes a lot of time, and capital Pi theta is that planning process, which is all this cross entropy method that we said that uses our current policy and samples also some other trajectories and uses the current dynamics to instantiate from action sequences, state sequence and rewards and the queue and computes the trajectories, fitness scores and updates those and so on, and then results on some set of Gaussians, one for every time step, and then you sample from that. This is exactly the sample. And once you sample, what are you going to do? Because it's a training time, you're going to deploy your action in the environment, right? But I really like that planning at training time because it allows you to discover better actions, all right? Because you do a very methodic search of your action sequences by look ahead, all right? So this is very important. So here you just deploy in the environment. So this is the actual, what exactly happens, and then you add it to the buffer and so on. And so what are you going to do now? Well, you better update your model, I suppose. You update by, getting so here is your estimate of the reward and your estimate of your Q function and your estimate of what is the next Z and your estimate of your action, all right? And essentially you add all these together, the three terms that we saw earlier about regressing to rewards, regressing to the correlating feature of the next state, regressing to the right Q with a Q target, as well as backpropagating through the Q for updating the policy. Yeah, that's it. What do you think? And it has excellent results. It has really excellent results. Yes. So now one question they say is, how do you form targets for your Q value? I mean, you can really, do planning and look at the final, state and estimate the Q, the goodness of that state, and use this as a target. But they say this is very, very expensive. So we're just going to form the usual Q targets. Okay, let's see. So this is the benchmark that they're using. Some is manipulation and some is robots. Just to be clear, for this set of experiments, the state representation is not sensory. There's no image. Essentially, you have a small vector that describes your state, the state of the dog, the state of this humanoid, and where the hammer is in the environment and where the nail is and so on. Okay, so it's as if you have perfect perception, and not only perfect perception, but also you have isolated the parts of the state that you think are relevant for the task, and you have a tiny little vector, okay? And this is what you feed in your learned dynamics model. Still, they say, instead of just predicting that vector directly, it's useful to jump to a even succinct latent space and do whatever we just said, that the Z that we just discussed. Now, the good thing about this, so this guy is SAC, soft actor critic. Soft actor critic is a model-free method, right? I mean, okay. Well, it does better, all right? So SAC is the blue. I would say, I mean, I really would like to know what happens much later in training, but TDMPC does very well early in training. Now, let me ask you a question. Was the model of the environment deterministic or stochastic? Deterministic in that case. Other suggestions? What is a stochastic dynamics model? It's a model that, conditioned on a state and action, it can predict multiple possible feature vectors. You can sample from it a feature vector for the future. So there is sampling there. It tells you, okay, this can happen or that and that. It doesn't reactively predict the representation for the next state. Here, what do we think? That the dynamics model was stochastic or deterministic? Deterministic? Okay, so it was deterministic, and the truth is that these environments indeed are deterministic, right? So with enough training data, the model should not, make any mistakes ever, because there is zero aleatoric uncertainty. Like the environment is itself deterministic, and with more and more training data, the epistemic uncertainty goes down, and your dynamics model, becomes very strong. And then, I don't see why your performance would saturate, right? Like you are not upper bounded by the dynamics errors. Now, here is another extremely interesting result that is very, very typical. And this happens also in the Go papers. So you can train yourself, and at training time, because you don't have much time, it cannot be that during planning you can look ahead. Your age can be super large, okay? You use some truncated age, let's say 40. Now, at test time, you can go and increase that horizon, and actually you'll do better. And at some point, okay, it saturates, to be honest, at some point. Okay, this is cross-entropy iterations. Do you see? So you were training here, you increase, you do slightly better. Okay, so basically the budget has to do with what is my horizon, as well as how many iterations of CM am I doing, or how many trajectory proposals. Okay, so the budget has to do with number of iterations, as well as the horizon of each trajectory. Do you remember that we said exactly the same thing with the offline Monte Carlo research? You remember the divers problem, that our horizon was not long enough to understand that 6 divers saving is a huge reward? Okay, yeah. So now the truth is the following. Although with ground truth models, this dramatically, just keeps improving the more you plan, with learned models, at some point, the errors compound, especially in non-deterministic environments, where you have the problem of also aleatoric uncertainty. Okay. Yes.
For the previous chart, exactly are the star on the axis?
Yes. So this is what you trained on, what they trained on in the paper, and then they say, okay, let me test it also with, increasing the horizon and giving it more budget at test time. Okay. So I train with some parameters, and then I test by increasing the budget. And look, it's not that things fail. I can, yes.
Why is the horizon different from default?
Why is the horizon different than?
From the default, the star and the X. So the iterations, the planning iterations. This also just the horizon.
Yes. So horizon and iterations have nothing to do with one another. So this could also be like 10 to 15, right? So it depends on how many iterations you want to do. Okay. And this is just the H, the capital H. The number of iterations is the capital J. Very different parameters, just and it being similar ranges. Okay. Okay. So check now this slide, guys. They say, now we're going to apply exactly the same process, but the input will be images, will not be low dimensional state vectors. Is that clear? And they say, when you have low dimensional state vectors, what are you going to use? What neural network are going to use to go to let's say, a latent feature? You're just going to put some MLP, multi-layer perceptron. If you have images, you're going to put a CNN or something like this. And they say that's all we change. And then we have competitive performance of image-based reinforcement learning. And here, this is very interesting because this is the soft actor critic from state input. And this is soft actor critic from pixels. And you see that from pixels, constantly the performance is much worse. Okay. This is curl. And we're going to take this we're going to see this in the future lecture, where we're going to have a specific dedication to image-based RL. And we're going to show that essentially the only thing you need is augmentations. So curl just considers tons and tons and tons of augmentations of your images, and then says, okay, this original image and the augmented version need to have close feature representations, and that's all. And you see, you get pretty good performance, right? DRQ, I'm not exactly sure what it is. Planet is kind of old-fashioned, but the Planet, the Dreamer, V1 and V2, we're going to see in the next lecture. This is mu0, and okay, you may think that this is a little bit pathetic, but efficient 0 is very similar to this. And you know what? The only thing that it does is the consistency loss. That's all. So the amazing thing with mu0 is that the only way they train their latent embeddings is by predicting rewards, actions, and Q values. And they didn't have this consistency of saying, you know what, if you encode the next state, the latent vector better be close to what you predicted. And actually, we're going to see this right next. And this efficient zero essentially is copy-paste that, but with that efficiency. And you see that efficient zero is actually slightly better than this guy. Why? Because it has a better planning procedure. It has a tree-search planning procedure, which we'll discuss right next. I mean, there are also a couple of other tricks over the mu0, but that's pretty much it. Okay. Yeah, I really like this because these are all very state-of-the-art methods, so which we're visiting and so on. Yeah, so they say you can trivially change it to any input that you like. Here, for example, you can also add proprioception, which means how am I heading? Like, what is the pose changes of my agent and so on, along with the images, and nothing changes, only the representation that jumps into that latent space. I think this is another tremendous benefit of latent space dynamics models. Okay, you just change the encoder, you have the other latent space, all the other losses and planning procedures and so on stay the same, right? Yeah. Okay, sure. So the same time to solve, but with less data and so on, and you can check more from that link. That's it. I thought that's pretty strong paper, pretty well explained also. So I really hope that you can, look at it in detail, all right? Because then we may add some questions to the quiz. Okay. All right. So now we go to our next awesome paper, which is mu0. Okay. And this is based on a presentation from DeepMind. The slides are based on a presentation from DeepMind. And just to remind you, so by the way, do you have any questions on the previous paper? Yes.
In general, do model-based encodings ever have any semantic meaningful encodings, or they just like interpretable by the machine?
Yeah. Say it one more time, your question. Yes. One more time.
Do the encodings ever have semantically meaningful things? Like, for example, in the running thing, would one of the encodings be like my current velocity estimation?
Yes, very good question. This is a very good question. So your colleague is saying, what do those latent features capture, and do semantic representations emerge on those features? Of course they emerge. And in fact, we're going to see, I mean, the truth is that those feature representations are super compact, so very, very hard to interpret. But for example, on Monday, where we're going to see different latent vectors holding the non-deterministic part of the state, you see that one latent vector learns about, let's say, location of the agent. The other can learn about location of the monster and so on. The best way to interpret what the representation is learning is by having an attention encoder. So then you can clearly see where the attention of the network is, like in which part of the image and so on and so forth. Do you see what I mean? No, but this is an excellent question. Another thing which I would be very curious about is the following. I mean, we know a lot about computer vision, right? So when you show me an Atari image, for example, in Montezuma's Revenge, right, where there's a guy goes up the stairs and turns left and there is a cave, why should I take that image and condense it into one vector, given that I know about caves and I know about stairs and I know about tunnels, right? So I come there with my priors as a human player, and I already know that in the tunnel you're supposed to go in, and in the stairs you're supposed to go up and down and so on. And that's why I can play so fast, right? That's why I can learn to play so fast. And you, that you don't use any of those semantic knowledge, you don't transfer anything, and you start your encoding from scratch, of course it's going to take you forever to learn something. And not only is it going to take you forever, but then you're going to go to another game where again there's a staircase and you won't be able to transfer any knowledge. Do you see? Because you haven't built a modular semantic, as you're saying, representation of your components of the environment, as opposed to condensing the whole frame into one thing. Do you see? So So basically, here's the thing. In this lecture, we're all the time talking about the planning and the dynamics and so on, while the biggest, let's say, importance is on that encoder, all right? And how that encoder can capture the state into a disentangled way. And then you'll have dynamics models operating on that disentangled states and being disentangled. And I want a different dynamics model for my staircase and different for my tunnel and a different for the red monster. Much like when we think of the master, we don't entangle it with the tunnel. Like, do you see? So that's how humans are able to dramatically compose things that they know and act well under novel compositions and dramatically transfer knowledge of dynamics from one environment to the other, right? So that's why our dynamics models right now help us to learn with less interactions, but don't help us to generalize. Because in the new environment, you again need to learn that dynamics model from scratch because the dynamics model tackled everything, all the elements of the environment. Okay, so dynamics models in the present way they are represented and trained and wired the network do not help generalization. And that's why I really love that paper. What is the role of planning in reinforcement learning? And they show, no, if you plan, you are not going to generalize better. So there is this huge confusion on people about, how planning is going to help you adapt to new environments. No, they're not going to help you adapt because you actually didn't transfer any knowledge of your semantic entity. It's precisely what you're saying. Does this make sense? Yes.
So to generalize better, you need to train a model across multiple data sets then, correct?
Well, sure. To be honest, that's not how I generalize. For example, I may never play Montezuma's Revenge, but I know, as I just said, about caves and the different entities, and I'm able to transfer them. So do you see? So I didn't train one dynamics model jointly across environments. When you're a kid, you just see one environment, your playroom, that's it. But your representations are modular and disentangled, and you are able to transfer them. Does this make sense? Yeah. It all has to do with how your representations are modeled and how disentangled they are and modular. Okay?
Okay, that's really interesting. Yes.
Yeah. So our next week, probably not Monday, but Wednesday, we'll talk about graph networks. Okay? In graph networks, our state will be a graph. Okay? And I really think that this is a very central key research topic. Better encodings and for representations and dynamics for, let's say, acting in the world. Okay, so we'll see some research about decomposable modular state representations coming week. Okay. Well, okay. So far, this other paper, which also I love, again, it entangles the state. All right, but it doesn't matter because it solves other problems. Yeah. So we said two things. We said that we like search process, and we also have neural networks, and specifically neural networks have two forms. One is the value network that take the input and spits out a scalar. How good is my state? And I use this to reduce the depth of the search. You remember alpha 0 doesn't even unroll to the end. Do you remember that? You go on the tree leaf and you apply your value network and you get your estimate and then you push it back to your nodes internal of the tree. And here is your prior network. You can call it also the policy network. Will help you to prune the breadth of your search. You don't need to try a lot of actions. Okay, you don't really need to try a lot of actions. Only the ones that are suggested from, your policy network gives some reasonable probability on. By the way, your colleagues had a very good question last lecture. He said, why do we sample the actions based on the frequency on the root? This doesn't make sense. Why don't we just follow the Q estimates? So do you agree? So we can look at the Q estimates of all the actions at the root and just take argmax of Q, correct? Why don't we do that? This has to do with action selection at the root, right? After the planning is done. Actually, let me show you exactly what I mean. Yes. So what alpha 0 did is he put the planning in during training time. This reminds us extremely the previous paper. At every state to take an action, you go through that research process. And, at the root, you have a distribution over actions based on how many times each action was visited. And you sample the action that was visited the most, or you sample from that distribution. And your colleague asked, why do we need to look at the frequency distribution? Why can't I just look at the Qs of the actions that I computed on my network? Does this make sense? I thought that was a good question, right? Yes?
This is during training, so we don't always have to do the best. We can sort of be a little off for the sake of learning what happens.
Right, but to be honest, at test time, we also do the same. We sample based on frequency visitation of the actions at the root state. Right, because the cool thing about alpha zero is that's the same thing at train and test time. Very simple, right? Yeah, any suggestions? Yeah.
Maybe like if you are looking at like rollouts, like you're a little bit more informed with just like the base key values and like just like
If you're looking at rollouts, what do you mean?
Like the distribution of actions that you like took as you were like trying to like search for.
Yeah.
Whatever you might get out, like you're a little bit more informed with just the key value that you're giving.
Yeah. Okay. So maybe I can help saying the following thing. You have your prior network pi theta, all right? And the truth is the following. Pi theta does not allow you to sample actions that have very low probability under that prior. So the Q estimates that you form for those actions are not good, okay? Because you just sample them less. So sampling based on the highest visitation means that, yes, I know about that action. And naturally, because UCB, I just use the UCB, clearly also has high Q, of course, and the prior and everything. But essentially, we saw a paper from ICML that shows how sampling from that frequency distribution is essentially an approximation to a very well-defined problem, which is sample based on the Qs, but without deviating too much from your prior policy. Because if you deviate too much from your prior policy, you're going to land in actions that actually you don't have a clue about because you actually sample them extremely little during training. So that's it. But you don't need to worry too much about this. What we need to worry is the following. This is all great. Alpha zero is exciting, but it uses ground truth model of the environment. Can we do exactly the same thing with a learned model of the environment? Okay. And if we do that, are we going to play worse? Can we still beat the champion? That's the question, right? Okay. All right, great. So I told you about this stress in the community that was there like a couple of years ago. Do I predict on the pixel space or on the latent space? And this was one of the first, because before mu0, of course, they had some prior paper, I think it's called the predictron, again from the same lab that says, forget about image reconstruction, forget about predicting pixels, just predict task relevant quantities. So the idea is exactly the same as what we saw in previous paper, just previous paper came later, all right? Which is from your latent feature, you'll predict your actions, your reward, and the value functions here, not the Q, but the value. That's fine. Okay, great. So here is a very nice required reading for our course, Mastering Atari, Go, Chess, and Shogi by planning with a learned model. So one model to handle all the possible games. You train, of course, different model. I'm just saying one algorithm to do that everything. And the main motivation is do not reconstruct pixels, just predict what matters for planning, okay? So let's try to visit that paper. Again, we're going to do the same thing as in the previous paper. First, we'll assume we have a paper, dynamics model already, and we'll use it for inference of actions. And then we'll go back and see, okay, how does the training work? So first, we're going to visit the inference, and then we're going to visit the training. So let's see. So imagine that I have a model. So what I'm going to do with that model? Well, I'm in a particular state here. And what I'm going to do is I'm going to apply my representation encoder to jump to a latent space, which is here we're going to denote as S and not Z, which is fine. Now I jumped, and this is this is the blue. So this is the encoder, and now comes my dynamics model, and the dynamics model will be in pink, okay? And my dynamics model has a lot of components. Let me tell you what are the components. Well, okay, they split it in two colors, but it doesn't matter. So first, for every state, I will be predicting the value function and the policy. Okay, similar to before. And I'm also going to be predicting the next state and the reward that I'm going to get from that transition. And so that's it. And of course, the reward for Go, the intermediate rewards are 0. So this is only going to matter for the terminal states. But the values are non-zero, right? Because values are expected returns. So of course, you have an idea of how probable every state is for you to win the game. So this is what exactly the value function tells you. How good is that state for you if your goal is to win the game? And do we ever predict observations from the state encodings? And the answer is no, we don't. Nobody cares anymore. The images are only used at the edge. And actually the edge takes 32 concatenated images to jump to the latent state, which I think is a bit crazy. I think it's a lot of observations. Yeah. So let's see. So what do you see here? Well, what I see is that we're using this model to do a tree search. We don't sample trajectories anymore. We do a tree search. That's pretty interesting, specifically Monte Carlo tree search. I'm going and each time I reach to a terminal node and I look at the value function and I update and I do everything I did with my ground truth model of the environment. I do the same thing with my learn model of the environment. Is that clear? Is that clear? So now this is a tree search process using a learned model. So this means that the states are instantiated themselves from your model, okay? All right, so there is again action selection, yes.
How do you know the game terminates in the latent space?
Yeah, so we don't care about the termination of the so by the way, here it doesn't tell you how we learn the dynamics model. It just tells you that we just move. Oh, you mean so that we don't continue unrolling?
No, I mean that when you're unrolling the observations, you know that game terminates. But when you're unrolling,
no, you also unroll, for example, specifically because you're predicting the reward, right? That reward probably will be 0 for all the states that are non-terminal, +1 if you won, -1 if you lost, right? Do you agree? Yeah. Yeah.
I have a question.
Yes.
So for this model, it is deterministic. So
it is deterministic, yes. With deterministic transitions and discrete actions.
Yeah, so for the same observation, maybe my tree is always the same. And expanding this tree for always the same.
Yes, so for the same state and action, you're going to go exactly in the same place because this is a deterministic model.
And so how do you explain it is a tree?
Well, you sample different actions, right? You say, oh, what if I do that? What if, I mean, for AlphaGo, also it was a deterministic model, right? And the tree comes from the fact of, oh, what if I do, like, what is the breadth in our tree? Different actions that we play. What if I do this action? What if I do that other action? And so on and so forth. Do you guys see? And by the way, who selects the actions? Who selects what actions to play? Again, our UCB criterion, right? So the same things as before. It's just instead that the transitions coming from the simulator, ground truth, now they come from that learned dynamics model, as you said, okay? Yeah, why planning? Well, we know why to plan, but is this clear? That's the only change, by the way. How do we use the model? Well, we use it inside that Monte Carlo tree search process in the place of ground truth transitions. Okay. Okay. So let's see. Why planning? Well, for the reasons that AlphaZero does planning and for the reasons the preview paper does planning. Because when you have a particular policy and value function, if you plan, then you will land to better actions. The action distribution you're going to get at the root, if you sample an action from that action distribution, will get some more informed actions than if you sample from your policy networks directly. This is what we said. Okay, this is so it's the same motivation here. So how do we do that? Then well, exactly the same thing as before. We take our state and we search with a learned model, and we land in a particular distribution of our actions at the root. For where we sample, we said that we sample based on the visitation distribution of those actions at the root, and then we apply that action in the environment, and the true environment sends us now to a next state. Okay, and then again, I think through, I get a new distribution of action at the root, I sample, I apply that action in the environment, precisely the same thing we had in the previous paper. And not only that, but also we had very similar, I think they also use capital P to do the planning process that essentially, takes, as input the value function action spits out an action distribution from where to sample. And then you continue. And at some point, you win the game or you lose the game. Is that clear? Much like in AlphaZero. So these people add a little bit extra noise at the root node, make sure that we actually explore. I'm actually not sure if this was happening also at AlphaZero, but sure, at training time, you want to explore more, so you don't just directly, or basically what happens is you make your frequency distribution high temperature. So you increase the temperature of that softmax. So high temperature means that, all actions are highly probable, and low temperature means that you have one like really dominate. All right. So in the beginning of training, we really have a high temperature. Okay. And then what happens? How we're going to train the model? These are our targets, the values, the actions, and the rewards. Okay, that's how we're going to train the model. So learning the model is now the next thing. Okay, so now we just said, I'm going to start with the model. I'm going to do some research. I'm going to select on some actions. By the way, the model in the beginning, the weights are random. So clearly, everything's going to be random in your research. Clearly, okay? So your selections are not going to be great, but as you generate trajectories in the environment, you can, improve your dynamics model and go back and do it again. Now, the amazing thing is the following. You don't need to learn your dynamics model from your own experience. You can take experience from someone else and train your dynamics model. And the amazing, crazy thing is the following. There is a whole, let's say, literature on offline reinforcement learning, which started like 1 or 2 years ago. And we're going to have an offline reinforcement learning lecture. And, they generate a lot of papers. And then MuZero, which is that model-based paper, actually has state-of-the-art performance as an offline RL algorithm, which means what? You don't need to innovate. It's only one thing you care, to do correct model-based RL. Models can be trained from offline trajectories. They don't need to be trained from your own experience, okay? You can play the Atari game, I can log your actions, and I can learn the dynamics of the world, and then I'll use it for me to play, okay? So there's no reason that your dynamics model is going to start from scratch, let's say. Is that clear? Okay. So how we're going to learn this model then? So we have some ground truth trajectories from the environment. By trajectories, we mean state action, rewards, and so on. And what we're going to do is we're going to ground our model. Ground means the same sequence of actions that I applied in the real environment, I'm also going to fit on my mental model. Okay, so I have a sequence of actions and states from the real environment. I'm going to fit the same sequence of actions to my mental model. I get the corresponding states, and I will make sure that those states that the model generates and the actual states, they match. Okay, how do they match? Let's see how I'm going to do the matching. So here is how. So the policy, the actions predictions from the model better match the distribution coming out from the Monte Carlo step. Use the rewards of the environments better match the rewards that my model predicts, and of course the rewards specifically from Go are very sparse. And here is the value estimates. I set some target, meaning an end step target for my value, and I ask value predictions from the model to match those targets. Okay. Does this make sense? So basically, because I did that search, and then I sampled action from the environment, then I ask my model, given this state, to actually match the frequency distribution as the output of the Monte Carlo research process, okay? Which means what? You just have a soft cross-entropy loss, exactly like before, right? Exactly when we didn't train for the dynamics transitions, when you only trained your policy. We had exactly the same loss function, if you remember, right? We asked our policy to go close to the frequency visitation distribution. And so that thing was there before. And so here is the value prediction that comes out of your network. And here you set those targets for each intermediate state. And if you also have rewards, you also match them to the ground truth rewards from the environment. So whatever you see at the top, guys, is a true environment trajectory. And whatever you see at the bottom is a latent trajectory. Okay? And you try to get them to match without ever asking them to predict and match on their visual observations. So do you see? So you ask them to match on the task relevant elements, which is the rewards, the value function, and the actions that are being selected. Is this clear? Okay, what do you see missing here? So this G, by the way, is the transition, right? So it has a state and an action and spits out rewards in the next state. Okay, so this is precisely the dynamics part. And you know, this latent vector as well as the parameters, of course, of the G and the parameters of the H are all trained end-to-end from those losses because everything is end-to-end differentiable here, right? You have different submodules, but they are all differentiable. And so all the losses backpropagate to all the parameters of all those modules. Okay, is that clear? Okay, but what obvious loss you see missing here? That we had in the previous paper, yes?
That the encoding of the ground truth next state is the same as the dynamics.
Yeah, this is called the latent consistency loss, right? That would be pretty helpful, correct? Yeah, so I think they mentioned, look, we did it, but it actually didn't make any difference. The truth is that they have tons of money, they can use tons of experience, but it does help tremendously for less amounts of training data, okay? This is precisely the efficient zero method. So guys, is this 100% clear? This is an environment trajectory where every state is paired with a frequency distribution, okay, with a reward, if anything is there. So you take those guys as a target for your P's at every time step, as you see. You take the U's as a targets of your rewards, and then you take the values, these guys, those V's that you predict at every time step, better match, you know, sum of instantaneous rewards plus gamma and you know, the new with your own. So this is bootstrapping. You're using your own estimate to bootstrap yourself, okay? Is that clear? Now, at some point, you know, those U's are going to become non-zero once you go close to the game, and that's how the value functions are going to propagate, you know, earlier in the game. Is this clear? It's actually not very complicated. Any questions here? Let me tell you why I'm asking this. There is a homework 5 that is mu0, okay? So you will need to implement some of these things. I'm not exactly which part, I don't remember, but this is all about this, okay? Monte Carlo research with a learned model. So do you have any questions here? Yes.
Yes, I'm curious. So if I plan in the hidden space manually or compared to use a simulator with real simulator, so which one is faster? This one, the mental process done complete in the hidden space based on a dynamic model. Like previously, it involves a simulator.
Excellent. This is a very good question. So the amazing thing with dynamics model is that you can unroll tons and tons and tons of trajectories because you don't need to go through the latency of the simulator. Do you see?
Yeah, but then when I do the forward pass for a model, there's some kind of.
There is some, yes. You also pay a cost of the computation of the forward pass, and the question is the simulator the faster or yeah? I see. Well, let me check and double check. I would imagine that exactly because you live in the latent space, these networks are actually very, very. I mean, this is very expensive. This guy is very expensive because it goes from images to latent space, but these guys are very small. You know, these are all small small vectors, right? So what is heavy with neural networks? If you have images and they're huge and videos and you have tons of patches and you need to attend left and right, so then the capacity goes crazy. But if you just have short vectors of your states, at least this part, the pink and the green, probably are kind of small. Okay, but I totally agree. The H is very, very expensive. Okay, and is unclear, or at least I need to check to make sure that indeed, this is much faster than using the simulator. Okay, but because it's interesting, because 1980s, that other paper we saw with the car driving, it said training the whole network was much faster than rendering one image in the simulator. Do you see what I'm saying? So their simulators were extremely slow, but this is a great question actually. Okay, so here is mu0 at a glance. There is a planning process that uses a learned model. Okay, and then there is interaction with the environment where you collect, you sample from the results of your planning process and you collect real trajectories. And here is C, updating your model, grounding their real trajectories to your model and updating its parameters. So planning, my dynamics model doesn't change. Interacting, I'm just sampling actions from the results of my plans, right? At every time step, there is this planning. Learning the model, I just take now the ground truth environment trajectories and update the model parameters. So what are the results? Pretty wonderful results, okay? So as you see, of course, who is the competitor here? The AlphaZero, the one that uses the non-learned model, okay? And what you see is that, in the beginning, the blue goes low because mu0, has a, AlphaZero has a benefit of, the model being ground truth, but at the limit, as training continues, it actually, the learned model does very, 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 very well. And here it even surpasses. And I'm wondering if the reason for that is, of course, this R2D2 has to do with some very, very good model-free method. They compare here for Atari. But my point is, I think the reason it surpasses is because you have so much more capacity of unrolling way more trajectories, because it's much cheaper to use your own latent model than to using a real simulator. Otherwise, why would this be here happening, right? Okay, very good. So here it is. You don't need to go and Shogi and so on. You can use exactly the same things in Atari. And what we're going to see is that planning a training time is very useful. At test time, you may as well use your own policy, but we'll see. Yes, please. Yeah. So here it is. They're used, but we'll revisit this when we talk about offline RL. So basically, let's see how this works. You can take all trajectories and reanalyze them. They call this mu0 reanalyze. Okay, so they use that in this paper just to be able to squeeze more information for every experienced trajectory. So how does reanalyze work? You take your old trajectory of the environment, and then you go and you redo planning. And because your dynamics model now is different, the results of the plans are going to be different. The action distribution at the root is going to differ. So then you can sample new actions. Okay, so this is some trajectory that you generated a long time ago and is in your experience buffer. And these are new results for policy and value parameters at a later t+1. So now what can we do? You can learn from those reanalyzed trajectories. How do you think we should learn? First of all, we will learn to predict the results of the new planning process. Do you agree? We have the states, we have better action predictions. I may as well make sure I copy these better action predictions. The next thing I do, of course, I can imitate the rewards, no problem. Now, with values, there is a little bit of a problem because, unfortunately, you need to be using the V of a later time step here. I mean, okay, all this also makes sense. But the question is, which new do you use? You will use the V, the value function of the later time step T prime, right? This is your current value function. And hopefully, you'll be forming much better targets now because you have better value function. But here is one problem. This value function was developed when your policy was playing right now while this trajectory is from an earlier policy. So there is a little bit of inconsistency because we know that value functions depend on the policy that you play with, okay? So, but they say it's okay, you can still use it, no problem. But does this make sense? So this is exactly how reanalyze works. And so this is what is called off-policy value prediction. So here is your new targets and your instantaneous rewards, and the new of the later time step and so on. So you have new targets now, and then you update your value network based on this. And offline reinforcement learning can just use exactly mu0 reanalyze, and instead of using the earlier trajectories of its own agent, you can use trajectories of another agent. Do you see? Yeah. All right. So you have two different time steps, the time step where the trajectory was generated and the target network, which you're training at T double dot and so on. And so basically you have the actor and the learning and you iterate. And here is a huge buffer of reanalyzed trajectories. So this is actually very important. 80% of their trajectories were old trajectories. Okay, so essentially you use the few environment trajectories, you go back and you say, no, I shouldn't have done this. Now I have a better policy and value network. My search process will give me new results. So we can stop here, but I want to say that this mu0 reanalyze exactly because it has such a great offline performance. We will see it in an offline RL lecture again. On Monday, we'll talk about stochastic dynamics models, which we've never talked about. Okay, stochastic latent dynamics. So far, all the dynamics models that we've seen was deterministic. So on Monday, we'll see a couple of stochastic ones, which are very important for playing Atari, because in Atari, the environments are stochastic. Okay? So see you on Monday.